Hi guys, this is Dr. J here, and in this video we will continue our discussion on conformations of cyclohexane. So in the previous video we learned how to draw chair conformation of cyclohexane, and also we learned how to identify axial bonds and equatorial bonds, right? So in this discussion, in the discussion or in this video, what we are trying to do is that we are trying to learn this concept called ring flip, and after that we will also learn how to identify cis-trans isomerism using these chair conformations, and also we will do a couple of sample problems that could help you in being successful in quizzes and exams. Okay, so first thing that we are going to do is we are going to discuss this concept called ring flip. And ring flip is defined as interconversion of chair conformations, resulting in the exchange of axial and equatorial positions. So when you have a chair conformation, okay, this chair conformation can easily flip, or in other words, you can basically you can imagine this as holding these two carbons, okay, the one pointing up and one pointing down, and then you are basically twisting, bringing those two carbons to the opposite side. Okay, so this bottom carbon will go to the top, this top carbon will go to the bottom. If you do that, you are basically flipping the whole ring, and when that happens, all the equatorial bonds, the blue bonds, all these equatorial bonds will become axial. Okay, so in this particular ring, okay, in this conformation, okay, in this ring, the blue bonds are actually equatorial, right? So the blue bonds are equatorial, and once the ring flip happens, they become axial. So they become axial. Okay, so in here the red bonds are axial, and after a ring flip, axial becomes equatorial. So here's the thing: you might think that, okay, I just barely learned how to draw the cyclohexane ring in one way, and now I have to learn how to flip it, right? So most people will be like really confused and might not wanna might even give up. It is like too much work, right? Learning how to draw two different rings and all the axials and equatorials, so that might be too much work. But there is a shortcut. Rather than learning how to draw chair conformation in two different ways, you can basically do a shortcut. Let me show you how. So in this shortcut, what you do is you basically draw the same chair conformation. Okay, so same thing that you learned in my previous video. Okay, so here is the chair conformation, and the carbons that are pointing up will have axial bonds. So here are the axial bonds, and pointing down will have an axial bond going down. Okay, so these are my axial bonds, and then remember, after a ring flip, all the axial ones, the ones in red, should go into equatorial ones. So these axial bonds are actually equatorial before, right? So these should be blue in color. Now, okay? Because these were equatorial before. Now they are axial, but they were equatorial before. Excuse me. Yeah, so these are equatorial. These are axial now, but they were equatorial before, and the remaining ones are actually axial before, and now they are equatorial. Okay, here are the remaining bonds, and they are equatorial, of course, and they were axial before, but now they are equatorial. Since they are axial before, they were red in color, so let's color them in red. Okay, so take home message: you don't have to learn two different ways to draw the same cyclohexane ring. All you need to understand is that after a ring flip, whatever you had in the axial position will go into an equatorial position. Whatever you had in the axial position we'll go into the equatorial position. Let's replace this hydrogen with something like maybe CH3. Okay, so that's a methyl group. So let's have a methyl group. So it was in it is in axial position in this diagram, but after a ring flip, the CH3 will go to an equatorial position. Okay, so that is as easy as basically picking any equatorial position and then putting it there. Okay, if you don't like this position, you can pick this position. Okay, maybe this position, it doesn't really matter. Okay, erase these and then put CH3 here. Okay, and then the other thing should be a hydrogen. Okay, this should be a hydrogen. Okay, so pick any equatorial position, erase it, and put the CH3 there. Okay, so that is as easy as that. So ring flip will basically change all the axial groups into equatorial groups. All right. Next, I want to see if you could try this worked example. Okay, so if you can, please pause the video and see if you could do this by yourself. All right, so in this example, okay, I want you to draw two different chair conformations of trans 1,4 dimethyl cyclohexane. Okay, so I want you to draw two different conformations of trans 1,4 dimethyl cyclohexane. So it's a cyclohexane, so you need a 6-member ring. Okay, but of course I know it's chair conformation. I'm just stating the things that we need to know. Okay, and then it's 1,4, right? So 1,4 dimethyl. So you have two methyl groups on number 1 carbon and number 4 carbon. This is a methyl. This is a methyl. And the thing is that they are trans. Okay, they are trans, which means if one methyl group is on the top plane, the other methyl group should be on the bottom plane, right? So if one methyl group is on the top plane, the other methyl group should be on the bottom plane. So if you use a wedge in one, use a dash line for the other. Okay, so but I know in the question it is asking us to draw two different chair conformations. So this is what you need to draw, but in chair conformations. So without thinking anything, draw two chair conformations. Okay, so here is one. Now, I mean, you should be able to draw them fast if you have been practicing them. Okay, all right, so these are two different chair conformations, and the two carbons of interest is 1 and 4. So here is number 1 carbon, number 4, number 1 carbon, number 4. Okay, so those are the two carbons of interest. Okay, so count around and see if they're 1 and 4. Okay, 1, 2, 3, 4. All right, so those are the two carbons of interest. And then we need methyl groups, right? So if we put one methyl group on top plane, excuse me. So if I put one methyl group on the top plane, okay, you don't have to write CH3. The other methyl group should be on the bottom plane. Okay, so in here, both CH3 groups are axial. Okay, in this case, both CH3 groups are axial. But next, what I'm going to do is I'm going to put the CH3 group on this carbon pointing down. So it is an equatorial one. Okay, this is equatorial. So this is going down. So the other CH3 group should be going up, right? So here's the CH3. Okay, in here, both CH3 groups are equatorial. Okay, they are both equatorial. Okay, so in here both are axial, in here both are equatorial. But these are the two chair conformations. Okay, these are the two chair conformations that you can draw for trans 1,4 dimethyl cyclohexane. Once again, why is it trans? Because when one CH3 group is on the top plane, the other is at the bottom plane. When one is on the top plane, the other is at the bottom plane. Okay, so that is how you solve these type of questions. If you want a little bit more practice, you can try to draw these two chair conformations. Okay, so pause the video and try this one. In here, what I want you to do is I want you to draw two chair conformations for cis 1,3 1-chloro 3-methyl. Cyclohexane. Okay, so this is the compound that you have. Okay, it's a cyclohexane, and you have a chlorine in number 1 carbon, and 3rd carbon has a methyl group. Okay, so we have to worry about the cis and trans, and this is a cis, so that means both chlorine and methyl should be on the same side of the ring, right? So if you are using a wedge, use 2 wedges. If you're using a dash line, use 2 dash lines. Simple as that. So this is what we have to use. We need 2 chair conformations. Okay, so let's draw 2 chair conformations. Of course, here is one. Here is one chair conformation, and here is another chair conformation. See, I'm not thinking about anything. I'm just drawing 2 chair conformations. And then identify the 1 and 3 carbons that you would like to use. Okay, I will use, I will use this carbon as my number 1 carbon, so you can go any direction. So 1, 2, 3. This is my 3rd one. So 1 and 3, okay? So that is understood, right? Okay, and then on the number 1 carbon, you can put chlorine. Okay, chlorine. So I'm going to put chlorine in the axial position. Excuse me. I'm going to put chlorine. Let's put it in the equatorial position. Okay, don't think about anything. Just put chlorine in the equatorial position. Is this chlorine? Answer this question. Is this chlorine on the top plane or the bottom plane? It is actually at the bottom plane, right? It is at the bottom plane. So when you are putting CH3, you should also put CH3 on the bottom plane. So this will be your CH3. So both your substituents are in equatorial positions. This is equatorial. Let's put E. CH3 is in equatorial positions. But let's say you went with the axial position. Okay, so you went with chlorine on the axial position, and it is on the top plane. So this is 2nd, 3rd carbon, and 3rd carbon should also have the methyl group on the top plane, because both should be on the top side, because this compound is a cis. That is key. Okay, so in this example, both substituents will be on the top. And the other important thing is that they are both on axial positions. This is axial and this is axial. All right. So why am I identifying the positions? Because honestly, the one with both substituents on the equatorial position is more stable. We will talk about it in more detail in the next video. So let me know if you guys have any questions. Okay. You guys have a good one. Take care.